Hi. So last time we spoke, I was explaining how we were using z mod pz as the coordinates for an elliptic curve. And part of the rationale was that working in a discrete coordinate system, like the integers mod a prime p, lets us set up a difficult discrete logarithm problem, which is the basis for modern encryption. Today I wanted to talk about what are the technical requirements we need from a coordinate system. So the integers mod p are not the only coordinates that you might use in an actual elliptic curve environment. And the type of coordinate system that we need is something that mathematicians call a field. So this word is different from the more colloquial field of study, right? This is a specific algebraic structure. And the rules for fields are built up from the same rules that we saw working with abstract groups. Now, the way that these things tend to play out in modern algebra is that the more rules we impose, the more it looks like regular old algebra with the real numbers. So groups are kind of this strange idea of, okay, I've got some kind of operation, but it might not even be abelian, right? We saw some strange groups like the dihedral groups, where the order that you take different elements in changes the result you get after combining them. So fields have more of this familiar structure, which makes them nice to work with. Let's go through the technical definition, and then I'll give you some examples we can look at. So this is the definition of a field. It is similar to the way that we defined groups. So a field has a set of elements, and I'll call this set F. And I've gone ahead and I've typeset this with the Blackboard bold that I've been using for special sets like the integers Z, the rational numbers Q, the real numbers R, and the complex numbers C. So F is going to be the set of our elements, and fields have two operations, where we saw before that groups have one operation. So these are the rules. First off, the set F has to form an abelian group under the operation plus. And the identity element for plus will be the element 0. So fields have so much of this familiar structure that we will always call our operations plus and times, and the identity element for plus will always be 0. And the nice thing about this is it is an abelian group, which means that just like regular addition that we've all grown up with, the order that you add things in does not change the result of your calculation. Rule number 2 is that the non-zero elements of F also form an abelian group, this time under the operation times, and the identity element for the times operation is going to be 1. So again, this is just like the multiplication that we've all grown up with. The order that you multiply two different things in does not change the result of your calculation. 1 times anything, call it x, gets us back to x. And any non-zero element has some multiplicative inverse, right? This is the way that we are going to handle division. We'll just say that there's something in there, we can multiply times x, and that will get us back to 1. The third rule is the distributive law, and we're just saying that, once again, parentheses work the way we would always expect them to. And this time, because we have two different operations, I've done the usual thing and I've said that elements just written next to each other implies a times sign. So A times the element B plus C is the same calculation as what we would get by taking A times B and adding that to A times C. And likewise, if we take the element A plus B and then we multiply by C, that would be the same calculation as taking A times C and adding to that B times C. So standard sort of stuff. There are more of our familiar rules here. So these algebraic systems behave more and more like systems of algebra that we've been practicing since elementary school. And I'll make a note here that, of course, anything times 0 is going to be 0. The reason for that is because of the distributive law. That's a fun little proof if you want to work out a proof in your spare time. Let me get to some examples. So there are several important fields that I imagine, we've been talking about a while now, and I imagine have come up in your earlier classes as well. So these are some of the algebraic systems that get special letter names for their sets. The rational numbers, which I denote with this bold Q, form a field, right? Addition and multiplication are exactly what they usually are. The identity element for addition is 0. The identity element for multiplication is 1. And anything that is not 0 has a multiplicative inverse, right? We just exchange the numerator and the denominator. And so the rational numbers are a very familiar field. The real numbers, right? R is the set of real numbers. These also form a field. The way that we invert a real number isn't as clean as it would be in the rational numbers, but we know that it still exists. We can always calculate 1 on x, so long as x is not equal to 0. And the addition is abelian, and the multiplication is abelian, and distribution law works. It's a very nice system of algebra to work in. And once again, the complex numbers also form a field. So a complex number z has a reciprocal, 1 on z, so long as z is not equal to 0. If you've seen complex numbers before, you've probably seen conjugation formulas for actually calculating 1 on z. That's not really the focus of this class, and we're in the final week of new material, so I'm not going to dwell on that a whole bunch, but that exists, and again, it's a nice field to work in once you get used to it. In order to contrast these, I'm also going to give you some non-examples. So none of the sets on this page form a field for various reasons. So first off, the set of integers is not a field. The integers have regular addition, plus the integers have regular multiplication, times, but the integers do not always have multiplicative inverses. The multiplicative inverse of 3 would be 1 on 3, but we know that that's actually a proper fraction. It's not an integer. So even though the integers are an important set and they get the nice bold letter for their set name, they're not a field, right? They just aren't. There's a name for what they are, but that's not the point of this class. Another example, so you may not be familiar with this notation. This M subscript 2 by 2, parentheses R, this is the set of all 2 by 2 matrices with real coordinates, right? So you've got some matrix A, B, C, D, and A and B and C and D are all real numbers. That's the set that I'm talking about. And if you've done linear algebra, then you know that there's actually an addition we can do on matrices, and there's a multiplication we can do on matrices. So this has two different operations, and there is a zero matrix, the matrix consisting of all zeros, which is the additive identity. And there's what we call the identity matrix, right? The coordinates 1, 0, 0, 1. Multiply that by any matrix, and you'll get the matrix that you started with. So that's looking good, but this set is also not a field because there are some matrices which are not invertible. So in this setting, we don't use reciprocals anymore. We wouldn't say 1 divided by the matrix A. But we can still talk about inverses, and the fact of the matter is that some non-zero matrices just don't have an inverse, and for that reason, this set is not a field. My final non-example is going to be a vector space. So R3, you can think of three-dimensional Cartesian space in X, Y, and Z. You can think of that as a space of vectors. Take your pick. So working in three-dimensional space, we have regular vector addition, where you take two vectors, line them up tail to tip, and that gives you coordinates for a new vector. And there is a zero vector whose coordinates are all zeros. Adding the zero vector to anything else, call it x, just gets us back to x. And there's even a form of multiplication on these vectors in the cross product. But the cross product does not have an identity vector. There's no vector that you can take the cross product of any vector v and get back to v. So for that reason, this vector space is also not a field. So when we're performing elliptic curve calculations, I claim that we can use any field as the coordinate system for our curve. We'll still be using some equation, y squared equals x cubed plus ax plus b. And the curve will consist of all of our coordinate pairs, x and y, that satisfy the equation. And as long as we are in a field, we'll have all of the necessary algebraic tools in order to do elliptic curve cryptography, just that some fields are better than others. Just for exposure's sake, I want to talk about some more exotic fields. So a very exotic example would be the q-adic, excuse me, the 7-adic numbers. There's a lot of theory that I'm shoving under the rug for this. It's just important to know that these exist. The seven-adic numbers are written in base 7, so our digits will be 0, 1, 2, 3, 4, 5, and 6. And what makes this set special is that our decimal expansions, or our base 7 expansions, can go infinitely far to the left of the decimal point, which is not something that we're allowed to do with real numbers. So in this expression here, this is my decimal point. So I've got a 1 in the ones place, a 1 in the sevens place, a 1 in the 7 times 7 is 49's place, and a 1 in the 7 times 7 times 7 is 343. So I have a 1 in the 343's place, and so on. I have a 1 in every position to the left. And I have a 0 in the 1/7 place, a 0 in the 1/49 place, a 0 in the 1 on 343 place, and so on. The reason why we're allowed to do that is because Q7, seven-adic numbers, has a different form of absolute value. So the absolute value of 7 is actually 1 on 7. So these decimal places going off to the left are getting smaller and smaller in value. And going to the right, they get larger and larger. I'm not going to prove this, but I claim that this number that I have written here is actually the seven-adic expansion of the regular old fraction 1/6. That can be a fun little exercise using the geometric series formula. The reason why we give this set the name Q subscript 7 is that every single fraction is contained in here along with new numbers. This is the same way that every single fraction is contained in the set of real numbers, along with some new numbers, the irrational numbers. So if you go on to use these sorts of techniques, it'll be important to know that every single prime number p has its own system of p-adic numbers. So there are 2-adic numbers, there are 3-adic numbers, and so on. There is a lot to learn about those things if they are a useful tool to you. And I don't know exactly, what your use case is going to be, but this is another example of what fields can look like. Now let's get back to something more familiar. We've been spending nearly the entire term learning about this algebraic system, Z mod nz. Is it or is it not a field? So no matter what modulus n we pick, we have regular old addition, and we have regular old multiplication, but performed on the residues mod n instead of doing integer calculations. In order for this system to make a field, which again is what we need to do this form of cryptography, all of the non-zero residues, starting at 1 and 2 and 3, all the way up to n take 1, every one of these residues needs to have a multiplicative inverse. So this is a problem that we've looked at much earlier in the term, back when we were meeting face-to-face, and we learned that this can only happen if n is a prime number. And conversely, this always happens for prime numbers. So if we are interested in coordinate systems for elliptic curves, every single z mod pz is a field which makes it a valid coordinate system for doing elliptic curve calculations. So we've seen before that Z mod PZ is a bit nicer to work with. I've said things like Z mod PZ does not have 0 divisors, the same way that we can multiply things in Z mod N and get to 0 even though that none of those elements we started with was 0. That can't happen in a field because non-zero elements need to have inverses, and you can't invert away from 0. Like I was saying, the integers mod p are a nice field for doing elliptic curve cryptography in. We need the fact that this is a discrete coordinate system in order to guarantee the security of our system. And in the second part of my lecture, I'm going to talk about some other possibilities for finite fields. I'll see you in a bit.